Hello, my name is James McCloof, and for the AERO4842 design project, I'm building a Saturnian dust measurement probe. In the following presentation, I'll discuss my progress on the sensor up to the midterm point. Ever since Galileo Galilei first observed Saturn's rings in 1610, they've continued to puzzle and fascinate humanity. Although their exact origin remains uncertain, it is widely believed that the rings we see today are the remnants of an ancient Saturnian moon system. Locked within Saturn's rings are clues not only to their own origins, but also to the broader principles of planetary formation and the complex resonances that govern moon and orbital dynamics. The objective is to develop a sensor capable of measuring the mass, velocity, and kinetic energy of particles within Saturn's rings. These measurements will provide critical data on the rings' composition and dynamics, thereby contributing to a deeper understanding of their origin and of the fundamental mechanisms governing planetary and satellite formation within the solar system. The sensor is composed of two main parts, the laser/photodiode beam break and the piezoelectric detector. Incoming particles will travel into the detection chamber and trigger the laser beam break. This is event number 1. At a fixed distance from the laser beam, the particle will impact a piezoelectric detector. This is event number 2. The timing between the events will be used to measure the relative velocity, and the magnitude of the piezoelectric response will be used to measure the impact energy. From these measurements, the velocity, mass, and energy of the particle can be determined. The laser beam break operates on the following principles. At a known distance above the plane of impact, a laser line will direct light across the area through which particles pass through, towards a series of photodiodes. When a particle passes this plane, the amount of light received by the photodiode will decrease, and it will produce a change in current. Using a transimpedance amplifier, this small change of current can be transformed into a measurable voltage difference. Hence, the timing of this event can be precisely determined. Piezoelectric materials produce a voltage under applied mechanical stress due to the separation of charges and their crystal structures. The Saturnian particle measurement probe will use piezoelectric detectors to measure the impact energy of particles. From the impact with dust particles, the piezoelectric detector will produce a damped harmonic oscillating voltage at its damped natural frequency. This voltage is caused by the mechanical stress applied to its structure. The voltage response is proportional to particle momentum, and the squared voltage is proportional to particle energy. The relative velocity of the particle can be calculated using the timings from each of these events. And with this measurement and the energy of the impact, the mass of the particle can be determined. The sensor will be calibrated with impacts of particles with a known speed and mass. This will enable the system to measure the velocity, mass, and energy of unknown particles upon impact. The first milestone achieved has been the design and assembly of the sensor structure. Figure 7 shows the assembly of the sensor without the photodiode array quite yet. The piezoelectric detector is at the base of the detection chamber, and the laser line shoots across the plane of the particle's travel. Affixed to the sensor is the Arduino Uno microcontroller, as well as the breadboard. Figure 8 provides further details regarding the structural design. The following circuit has been designed to interface the piezoelectric sensor with the Arduino microcontroller. Key design considerations included: the resting voltage was biased to 2.5 volts since the analog input of the MCU can only read 0 to plus 5 volts. The voltages were also clamped to those 0 and plus 5 volt rails to protect the MCU. And the resistance and capacitance values were selected to ensure the time constant would remain small enough to adequately characterize the 2 kHz frequency response of the piezoelectric disc upon impact. To date, the software has been written that records the impacts of the piezoelectric sensor and updates the voltage response in real time, as well as performs an FFT on the analog signal. A triggering logic was designed such that the analog signal is stored to a circular buffer on the microcontroller until an impact is detected, and then it stores the rest of the response before writing it to MATLAB. So this buffer system has enabled 40 kHz sampling frequency, and Figure 10 shows the measured response to a grain of salt with an impact velocity of approximately 2.5 meters per second. Next steps will include developing the photodiode laser beam break circuit and tuning the transimpedance amplifier for an adequate response of the photodiode. Once this is complete, it will then be interfaced with the piezoelectric sensor to determine the velocity of the particle. Lastly, the sensor will be calibrated with particles of known mass and velocity before it can then be fully tested and verified. To determine sufficient testing conditions for the sensor, NASA's Cassini mission data was used to estimate particle kinetic energy. Based on these estimates, salt grains proved a viable testing particle, as we can achieve similar kinetic energies at velocities much lower than Saturnian's orbital speeds by using particles that are more massive than those found on orbit. Using millimeter-sized salt grains, the sensor should be able to detect and measure these particles with velocities ranging from 1 to 10 meters per second. These impact energies will be analogous to micrometer-sized particles within Saturn's orbits at their orbital velocities. This video shows a live demo with a salt grain with impact energy of 1 millijoule being dropped onto the detector. The voltage response sampled at 40 kilohertz is sent to MATLAB, which plots the data and calculates the frequency response. The salt is dropped, and MATLAB calculates the voltage response as well as the frequency response. We see a spike at the frequency response near the damped harmonic frequency, which is just under 2 kilohertz. The next steps would then be to incorporate the photodiode array so we can calculate the velocity and then back calculate the mass. Thank you for watching my midterm progress report. You may reach me by email with any questions. Thank you.